Hello everyone, my name is Dr. Harry Farwaha and I am the new CHEM 121 Beat Your Course instructor. So I'll just write my name over here. Dr. Harry Harry Farwaha. And I am the new Beat Your Course instructor specifically for CHEM 121. So just to give a brief introduction about myself, I have a Master's and a PhD in Pure and Applied Chemistry, and I have over 3 years experience ensuring that all level of undergraduate students are fully prepared for their assignments, tests, exams and beyond. So I have many years experience in education for chemistry undergraduate students. And my main strategy that I've developed over the years is to break down difficult concepts and tricky questions so that you feel more comfortable, more able, more confident and more prepared for your upcoming exam. And today I want to provide you with a sample of our upcoming CHEM 121 final exam crash course for Beat Your Course by going over molecular orbital theory. Now the reason I've chosen molecular orbital theory specifically, just to give you a sample, is it's one of the trickiest ones in terms of being very abstract and being kind of complicated, and some people do get kind of confused. There's not many calculations in this kind of topic, it's very visual. So what is molecular orbital theory? Well, just like valence bond theory introduced a higher level of theory than, say, VSEPR, molecular orbital theory is a more sophisticated and more accurate way to describe the electronic structure of molecules, and it ties in very nicely to some experimental observations that we see, which we will talk about later. So how do you actually come up with this molecular orbital idea? The way to do it is essentially a model that scientists came up with, and it comes from the combination of atomic orbitals, and that's exactly what we're going to do. We're going to take atomic orbitals, and we should already be kind of familiar with how atomic orbitals are arranged, and we're going to combine them all to come up with brand new molecular orbitals. Now luckily, it can be very tricky when you're dealing with complicated compounds, so we're only dealing with, in this example, two different types of molecular orbitals: homonuclear diatomic orbitals for second row elements, and also organic pi systems. So we have that over here, two situations. So I'm first going to talk about this first example over here, which is homonuclear diatomic molecules, and then I'll switch to organic pi systems, which some people find a little trickier. So we already know the definition of sigma bonds and pi bonds, but I do want to briefly overview this again, just to make sure that we're all clear about this. Another brand new concept is the idea of anti-bonding orbitals. So we should already know about bonding orbitals and how bonds like to form between the nuclei of two atoms, and they're stabilized by having electrons in between the nuclei. But you also have this new concept of anti-bonding orbitals, and they exist whenever you have a node between two atoms. So I've shown this in this example in this diagram over here. So a node is an area where you have no electron density. So a way to remember it is no electron density. And essentially, that's what you always see with anti-bonding orbitals. So what have I actually shown? What have I actually depicted here? A bonding orbital essentially is a constructive combination of two wave functions. And what that will do is form an even stronger wave function. So this is a sign of strength. This could have been, for example, a 1s orbital and a 1s orbital combining. So you could have two of these combining to give you a very big bonding orbital, which is located in between the atoms. So this bonding orbital, for example, between hydrogen, will be occupied between the hydrogen atoms. This is molecular hydrogen, H2. And the bonding electrons would occupy this area. So what about the anti-bonding orbital? Where would the electrons occupy here? As you can see, I'll highlight this in orange, we have a node. So let's ignore that. So we also have a node occupying here, and this is an area where you've split off the electron density. So what this means is, now our electrons are only going to occupy above and below each of the hydrogen atoms, for example. So you could have the electrons occupying either atom. So what this is really signifying if you fill up antibonding orbitals, it's actually weakening the bond. It's telling the electrons, don't go in between the atoms, go to either side of them. It's a form of localization. Of charge. So it could mean that the electrons either occupy one hydrogen atom or the other. You might ask yourself, why is that weakening the bond? And the answer is, if you have bonding electrons, it minimizes nuclear repulsion. So if you have two nuclei between two atoms, they will repel one another, but if you have bonding electrons in between those nuclei, it keeps everything together and strengthens the bond. So that's the central theme of this. Now we have a simple equation that you will use no matter how complicated the question gets, and that is the bond order. The bond order is a measure of how strong the bond is, and ideally, normally, in most situations, it's roughly equivalent to the number of bonds between the atoms. And it's the number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals divided by 2. So this is actually indicating something. Whether you have bonding or anti-bonding orbitals is kind of irrelevant because they're essentially like empty rooms. They only become activated when they start becoming occupied by electrons. So it really matters how many electrons are in the system because that will completely change the bond order of your molecule. So let's look at an example. Here we have hydrogen. Now hydrogen, as we should all be aware, the electronic configuration is 1s1 and 1s1 here. Now this is a completed molecular orbital diagram, and the way it's structured is you always fill in the left-hand side first and then the right-hand side, and the last is what goes in the center. The center is your molecular orbital. Molecular orbitals. And we can see that a 1s and a 1s combine to give you what is known as a sigma orbital. And this is a bonding orbital. And the anti-bonding orbitals, all anti-bonding orbitals always have a star, and we call this sigma star. And this is always what you see for anti-bonding orbitals. Anytime you see that star, that asterisk. So this is anti-bonding. There's two very fundamental rules for drawing molecular orbital diagrams. The number of orbitals you have is conserved. If you have one orbital for hydrogen and another orbital for hydrogen, you're only going to have two molecular orbitals. So I can write that down as well. You have two molecular orbitals because you have one for hydrogen and another one for hydrogen. Similarly, you can see that you had one electron for hydrogen and one electron for hydrogen, one here and one here, and you always fill up the molecular orbitals, starting with the lowest energy first. So you have 2 electrons in total in the system. So this is really adding things up. That's all it is. You add up the orbitals and you add up the electrons. You might ask yourself, why do I have 2 combinations? Well, as I've shown before, the bonding orbital arises because you have constructive combination, and the anti-bonding orbital arises because you have a deconstructive combination. So an anti-bonding orbital, a very simple way to show it, so this is really getting into why anti-bonding orbitals even exist. I can show this on the previous example as well. What we see here in this diagram is that you're adding a plus and a minus, and that's what's giving you an anti-bonding orbital. What does the plus and the minus actually mean? It just means you have different phases. and they're adding up like so. And if you add these two things together, you end up with no electron density. And that's essentially what an anti-bonding orbital is. So it comes from the addition of opposite phases. And that's higher in energy. So we have an energy axis here as well. And that's important. This tells us the order in which we fill up electrons. And that's the basis of Aufbau's principle. So that's the revision. So this was covered in previous topics, so you should be very familiar with Aufbau's principles. Very simple. Lowest energy orbitals are always filled first, and that's the exact same conserved for molecular orbitals. So, all the atoms and all the homodiatomic molecules are on the same energy axis. So what we can see is that we have a case where the bonding electrons are lower in energy and the anti-bonding orbitals are higher in energy. Now for hydrogen, it looks like we only have 2 bonding electrons. So a simple question would be, what's the bond order of hydrogen? H2. And I can show that on the right hand side here. You just use the same equation used before. Bond order is equal to the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. So that should be fairly straightforward. So BO, number of bonding electrons is 2, number of anti-bonding electrons is 0, and you divide that by 2 and you end up with a bond order of 1, which implies that you have one single bond between hydrogen and hydrogen. So hopefully that's very straightforward. So I've wrote this in words here. H2 has 2 electrons. The middle column of orbitals is filled with 2 electrons. It's always the same combination. Now the way that you might try and get tricked in your exam is if they give you a molecule with a plus charge or a negative charge. And that's actually deceptively simple. Whenever you see a negative charge, always think 1 less electron. And if you see a negative charge, you always think, let's highlight the negative, that's always 1 more electron. The diagram actually stays the same. All you're doing is you're either adding or removing an electron. Now, if you were to do the molecular orbital diagram for H2+, how would you do that? So let's say you had to do this. So if you had H2+, the way to draw molecular orbitals for charged molecules is you simply split it up. And now you know that you're going to add them anyway, so it doesn't really matter. You can say that this is going to be H plus a neutral H atom, hydrogen atom. And it doesn't matter which way around they are, so we can quickly show that. Just with a small diagram over here, same as before. So this is lower in energy, and this is higher in energy. Here you have a hydrogen, here you have a hydrogen plus, so you can see I've switched them because it doesn't really matter. And I can show the electrons in red. Hydrogen only has 1 electron. Hydrogen plus does not have any electrons, so all you're going to have is 1 electron in the bonding orbital. So that means the bond order for H2 plus will be equal to 1 take away 0 divided by 2. We don't have any anti-bonding orbitals and we only have 1 bonding, so our bond order will be 0.5. Now for H2 minus, you have an extra electron, and that comes from H minus and another hydrogen atom. You can show the same diagram, so the template is always fixed. Whenever you have the template, that's not the thing that's varying. The thing that's varying is the number of electrons. So you should just know the electronic configuration of all the atoms from previous topics, and that will always guide you on the right track. So here we have, I'll do H minus here just to really emphasize that it doesn't matter which one's on the left and which one's on the right, because the center is always the combination. So you have 1 electron, but you also have an extra electron, it's H minus. You also still have 1 electron for your neutral hydrogen atom, and that will give you 3 in total. So this is a slightly different diagram. Let's check the bond order. The bond order will be equal to number of bonding electrons is going to be 2. and the number of antibonding electrons is going to be equal to 1. And that will be divided by 2. So we end up with a bond order. So I'm not sure if that's clear, if that looks like a 2, it looks like a Z. Just want to make that extra clear. Divided by 2. And that'll give us a bond order of 0.5 as well. So for two different reasons, we have a bond order of 0.5 in both cases. So it looks like if you take hydrogen, whether you add an electron or remove an electron, it gets weaker because the bond order is lowering. So that's weaker if you add an electron. And it's also weaker if you remove an electron. You don't really need to think about this too much because you followed the routine. So this is something to be very careful of in molecular orbital theory. It doesn't matter too much the underlying concepts about why your answer is your answer, provided that you followed the procedure accurately. If you follow the procedure, you don't need to question your answer. You know that it's correct. The procedures are very fixed. The molecular orbital picture for hydrogen is fairly simple because you only had one orbital in each atom. It was only a 1s and a 1s. The same is also true if you have a 2s and a 2s. S orbitals, there's only one s orbital. So that's why it's fairly simple. Things start to get a little bit more complicated when you look at p orbitals. So we'll cover that next. So nitrogen, for example, we have, for nitrogen, you should know the electronic configuration of nitrogen, just as a little review, 2s2, 2p3, and for this nitrogen as well, the same thing, 2s2, 2p3. So these atomic orbitals are going to combine to give you your molecular orbitals. Now you have three orbitals, and they're both, and they're all p. So you have px, py, and pz. And as we've learned from valence bond theory, the three p orbitals combine to give you 2 pi and 1 sigma. So I can just write that on the side here. Px and the py and the pz always give you 1 sigma and pi and another pi electron. And if you want to know why, you'd really have to go back to valence bond theory. It's to do with the geometry. You're essentially adding the px orbitals. I can show the px orbitals are actually combining head-on. So there's a head-on overlap. So that's where the sigma bond comes from. And the pi comes from, this is actually going away and towards the plane of the paper. And this is essentially one of your pi bonds. And you also, so this could be your py's. So if you think of the x, y, and z axis, so this could be x, y, and z. So I've shown the x-axis p orbitals, the y-axis p orbitals, and you also have the z-axis p orbitals. And they form another opportunistic pi bond. So I can just show that. I can show the phases as well, just to really remind everyone that as long as the phases are constructive, as long as they're the same phase, you will always get an extra bond. These bonds are slightly weaker, they're just opportunistic, and they're above and below the plane of the sigma bond. So that's just a little reminder about why we have 1 sigma and 2 pi bonds arising from the combination of our p orbitals, and it comes from this axial combination. Right, going back to the diagram, how do we actually fill this in? Well, we have 5 electrons on the left and 5 electrons on the right, so naturally we're going to have 10 electrons in the middle, and that's exactly what we have. You might be asking yourself, why do we have this template where we have 2 pi's, a sigma, 2 pi stars, and a sigma star? You do not need to know this. All you need to know is that this is the template from everything from lithium to all the way to nitrogen 2, regardless of any plus or minus charges. So it doesn't matter if it's lithium 2 plus or lithium 2 minus, etc. This is the template molecular orbital picture, and the only variant are the number of electrons and the number of bonding and anti-bonding orbitals being filled up with electrons. So what have we predicted here? So we need to look at the bond order of N2. So what is the bond order? As always, the bond order of nitrogen is the number of bonding electrons that are filled up. So In blue, I'm going to circle all the bonding electrons. We have 2 here, we have 2 here, 2 here, and 2 there. We have 8 bonding electrons. So blue, I'll use blue for bonding. So we have 8 bonding electrons. How many anti-bonding? I'll use red for anti-bond. How many anti-bonding electrons do we have? We have 2 here. And that will be divided by 2, as in the general formula, to give us a bond order of 3. So it looks like nitrogen has this kind of structure, and it has 2 leftover electrons here and here, which are irrelevant. The only thing you need to know is the bond order, which is 3 in this case. Now, I've introduced a more challenging question. One thing they really like to do in these exams is throw you a curveball, take you out of your comfort zone. And I don't want anyone to fall for these kind of traps. So the key way to tackle this is to say, well, I'm going to stick to what I know. I'm going to stick to the same concepts regardless of the example given. And I'll try and figure this out. What do I know about calcium carbide? Well, any anion of that's associated with calcium must have a charge of 2 minus, because calcium always has a charge of 2 plus in an ionic compound. So that's the fundamental idea. So if calcium is always 2 plus, then C2 for this carbide anion must be 2 minus. So what you're really asking is asking how it's relevant to this page. We have to consider the molecular orbital diagram for C2 2 minus. So what is C2 2 minus? You can consider it to be a combination of C minus and C minus. Well, what's the electronic configuration for C minus? Well, carbon always has the electronic configuration 2s2, 2p2, so we should be aware of that. That would mean that carbon minus would have the electronic configuration of 2s2, 2p3. And for the other carbon, again, it would also be 2s2, 2p3. Now, we've seen 2s2, 2p3 before. This is in fact isoelectronic, or I can just say equivalent, with nitrogen and nitrogen. So that would mean, therefore, C2, 2 minus, must have the same bond order as nitrogen. So we can even put that in a square box to say it's similar to nitrogen. And the bond order would be 3. So this is for the bond order. And that should be fairly intuitive, because nitrogen is one element after carbon. It would have one extra electron. So that must mean that C minus is isoelectronic with nitrogen. So I'll just do that, I'll just write that just as a reminder. C minus is isoelectronic with nitrogen. So they might try and trick you like that. Like I say, they might add an electron or remove an electron. It doesn't really matter. You follow the same rules that you always follow. And to that end, I'm going to breeze through 3 examples where we have boron 2 plus, C2 2 minus, N2 2 plus, and beryllium 2 minus. And all you need to really think about is how do you want to split them up. As I've already mentioned, it doesn't really matter. So we'll take beryllium for example. I'll do beryllium in blue. So I'll circle this, and this will be our blue example. Sorry, this is boron. So boron has the electronic configuration 2s2, 2p1. Boron plus would therefore have the electronic configuration 1 less than that. It would just be 2s2. So what electrons would you have? You have 1, 2, 3 electrons for boron, and you'd only have 2 electrons for boron plus. So it looks like you have 5 electrons in the system, 3 on the left and 2 on the right. And all you do is you just add them up. And I can show the electrons in purple if you want. Doesn't really matter. And all you have to do then is read the diagram to know the bond order. So we need to know the bond order for this. The bond order, I'll do this in blue just to colour code a bit better. The bond order for N2, for B2 plus, sorry, the number of bonding electrons, where are they? Where's the bonding electrons? You have 2 over here, and you have 1 over here. What about the number of anti-bonding electrons? You have 2 over here. So 3 bonding electrons minus 2 anti-bonding electrons divided by 1. That will give us a bond order of 0.5. And the second example, we have, I'll do this in orange, C2, 2 minus. So we actually already had a look at that one. So just to emphasize this with a diagram, now complete with a diagram. So you can split this up into C minus and C minus. You might ask, why didn't I split this up into C2 minus and just a neutral C? You're going to add up the electrons anyway, so that doesn't really matter, as long as the electrons add up to give the same value. So carbon minus is 2s2, 2p3, so an extra electron, 2s2, 2p3 here as well. So we have 10 electrons in our system. So you can show that. 1, 2, 3, 4, 5. Notice how I'm filling this up. Hund's rule. I'm separating out all of these unpaired electrons, as you should do. You don't pair them up because they repel. They only pair up if they have to, if they run out of room. 10 electrons in the system. I'll do this in purple again. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And how many bonding electrons do we have now? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 bonding electrons. And how many anti-bonding? We only have 2. So the bond order in this example, which we already did, is going to be 8 minus 2 over 2. So we'll have a bond order of 3. And indeed, carbon 2 minus actually does have a bond order of 3 experimentally as well. Right, the next example. So now we have, what's the next example? It's nitrogen 2, 2 plus. So we can say that's a combination of a nitrogen plus and a nitrogen plus. Now I did say it doesn't have to be nitrogen plus and nitrogen plus. You can also have nitrogen 2 plus with a neutral nitrogen. You'll get the same answer regardless. So that's 2s2, 2p2 now. So you can say that nitrogen plus is actually similar to neutral carbon, isn't it? Because it's one before. It's 1 electron less. And if you fill up the electrons here, you have 1, 2, 3, and 4. And also the same on the right hand side, 1, 2, 3, and 4. And if you fill in the electrons there, I'll do that in purple, you'll have 1, 2, 3, 4, 5, 6, 7, and 8. So it looks like you only have 8 electrons. What's the bond order? Bond order. The bond order is equal to, how many bonding electrons do we have? We have 1, 2, 3, 4, 5, 6. We only have 6 bonding electrons. Minus how many anti-bonding do we have? In red. I've shown it in red. We have 2 anti-bonding. And divided by 2 from the general formula, that will give us 6 minus 2, so that will give us a bond order of 2. So it looks like dinitrogen with a plus charge, 2 plus, has a bond order of 2. And the last example, beryllium 2 minus, so I'll highlight that in green. So yeah, I'll just do the last example in green just to make it easier to see. So the nitrogen 2 example was in blue again. So that's what we've shown here. So the last one, beryllium 2 with 1 negative charge. So green, I'll stick to green for that one. So I can have my beryllium, and then my beryllium with a negative charge, which basically means an extra electron. Beryllium is 2s2, and that's it. And the other beryllium is 2s2, 2p1. One question I got asked was, why didn't I show the 1s electrons? And that's because the 1s electrons are completely filled up. So both the bonding and the anti-bonding orbitals will be filled, so they will just essentially cancel out, so you don't really need to include them. So we're starting with 2s just for the ease of simplicity. And on the left hand side you have 2 electrons, on the right hand side you have 1, 2, 3. Quite naturally you're going to have 5 electrons in the middle, and you just fill up as you always do. So now the bond order for beryllium. Number of bonding electrons is 1, 2, 3, just 3. And the number of anti-bonding electrons is 2. So 3 minus 2 over 2. And that will give us a bond order of 0.5. So essentially, no matter if it's a positive charge or a negative charge, all of the homodiatomic molecules from lithium all the way to nitrogen follow the same template, this template that I've shown here, and the only variant is the number of electrons and how that affects the bond order. Now, one way they might try and trick you, that you should bear in mind, if the bond order increases, then the bond length will decrease. And that should make sense. If you have a strong bond, you have a strong interaction, and anything with strong interaction will want to get closer to one another. So they might skip the bond order and ask you about the bond length. And that's easy enough. It just does the opposite of whatever the bond order has done. If the bond order has increased, you have a shorter length. And that's all you really need to remember. So, for example, I can say that N2, 2 plus, when this has a bond order of 2, this must have a shorter bond length than beryllium 2 with a negative charge, which is indeed the case. Now things get a little more complicated when you look at oxygen, and there's one main thing that has changed, and that is, if I highlight this, and I'll do it in yellow because I don't want it to confuse the diagram too much, not that yellow. I'll just do green actually. These two orbitals have switched. What are they? They are the sigma orbital and the pi orbital belonging to the combination of your p orbitals. And they've switched places. You don't need to know why. It's to do with the electronegativity of oxygen. Essentially, the sigma orbital, this sigma orbital, is now lower in energy because of oxygen's electronegativity. That's all you really need to know. I doubt they would ever ask that. All you have to know is to remember that this is the template structure for O2, F2, neon 2, and their ions, whether it's a positive ion or a negative ion. This is the template structure that you would always use for this. And we can ask ourselves, how do you remember this? How are you supposed to remember that oxygen, fluorine, and neon have this type of structure? If you look at the molecular orbital diagram for the p region, there seems to be this horizontal symmetry. It looks more ordered. It looks like you have one down there, two there, and one there. It seems to be a mirror image, and that's the way I like to remember it. You can think of the letter O for oxygen. It also has this horizontal line there. So that's the little cheat I use to remember. If it's oxygen or beyond, you have a symmetrical kind of region for your p molecular orbitals, the ones derived from p. Does anything else change? No, nothing else changes. The template's fixed, and you still do what you always did. You count the number of atomic electrons. So oxygen is 2s2, 2p4, 6 electrons on the left, 6 electrons on the right, 12 electrons in the middle. And they fill up beautifully as shown here. So, yep, 6 electrons and 6 electrons. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now this is the interesting thing to note. It looks like the last 2 electrons are singly occupied. So these are singly occupied electrons, and this is because of Hund's rule. Hund's rule says that the electrons will only pair up if they don't have a choice. So this means that O2 is paramagnetic. That's another question they could ask you. And as soon as you see paramagnetic, sorry, I keep deleting something I just wrote. If it's paramagnetic, all that means is you have unpaired electrons. And so all you have to do is fill up your molecular orbital diagram. As soon as you have any unpaired electrons, you would just say that it's paramagnetic. The question could easily say, explain why O2 is paramagnetic. All you do is you figure out the template, which is always fixed for O2, F2, and Ne2. Count the number of electrons and fill up the middle, and then you will see why it's paramagnetic when you fill up the electrons. And this is not predicted with valence bond theory. So valence bond theory predicted that oxygen would have this kind of structure, with a double bond there. However, that's not actually the case. The unpaired electrons implies that you have an unpaired electron in each oxygen atom. Now, we should bear in mind that the bond order doesn't change. These two are actually interchangeable, but this is the common one. This is the oxygen that we actually breathe in. This is the oxygen that binds to hemoglobin. The unpaired electron is actually what gives oxygen its versatility, its usefulness. This oxygen is actually toxic. So if you breathed in this oxygen, it would be very, very bad for your health. So that's something to bear in mind. What is the bond order of this? We can just do another bond order example to make sure that we're all bond order champions. And the bond order is we have 2 bonding electrons, and another 2, and another 2, and another 2. Looks like we have 8 bonding electrons. How many anti-bonding electrons do we have? We have 2 over here, and 1 here, and 1 here. We have 4 in total. So let's remind ourselves about what these orbitals are. This is sigma, this is sigma star, this is the pi star, and the pi star here, and lastly the sigma star up there. Back to bond order, it's 8 minus 1, 2, 3, 4 divided by 2, so we have a bond order of 2. And that was a question actually for the BYC concept clarifier, so I've essentially done that. What's more stable, O2 plus or O2 minus? Now for this, all you have to do is look at your diagram. So for O2 plus, let's see what's going to happen. We have one more, I'm going to write one more electron, but I want to be clear about what type of electron it is. What type of electron is it? So one more. One more electron, one less for O2 plus. If it's O2 plus, sorry, I was going to do O2 minus first. So one less electron. That doesn't give you all the information you need. For O2 plus, if you're going to have one less electron, it's going to be one less anti-bonding electron, okay? So you have one less anti-bonding electron. If you have one less anti-bonding electron, will that strengthen your bond or weaken your bond? I'm just going to pause to see if you can figure this out. If it's anti-bonding, if you're losing anti-bonding electrons, that's going to strengthen the bond, okay? Anti-bonding electrons want to dissipate the bond, so if you have less of them, that's better. So this will make it stronger. And if it's stronger, it's more stable. Now, if you look at the negative charge, you're going to have one more electron. And that will move, where's the extra electron going to go? It's going to have to move to the anti-bonding electron. So you're going to have to add to the anti-bonding. And if you add to an anti-bonding orbital, you weaken the bond. So, because we're talking about stability, stronger, more stable for O2 plus. And really, just to stretch this even further, if you lost both of these anti-bonding electrons, say if it was O2 2 plus, then it would be even stronger. The more anti-bonding electrons you lose, the better. The more you gain, the weaker the bond. So hopefully that will be clear. And that's as tough as it would get for molecular orbital diagrams for diatomics. They might try and trick you with an oxygen example because you need to know about when the orbitals actually switch places, but to summarize this, there are only 2 templates. That's the key thing to know. There's only 2 templates and you stick to them, and the only variant is the number of electrons you have for the example that you were given. Now on to something a little trickier. We're going to start talking about molecular orbitals for organic pi systems. We need to remind ourselves what a pi system is. Now the pi system is made up of leftover p orbitals, and for this you have to go back to valence bond theory. So for example, we need to look at sp2 orbitals. Where do sp2 orbitals come from? They come from the combination of 1s and 1p and 1p. And what do they look like? They look like a trigonal planar shape. They essentially look like this. So you can have one there, and it's going to be a triangle like this. Another one here, and another one there. So this is kind of a, it's not an ideal kind of diagram, but what this shows is that your SP, in fact I'll just for the ease of simplicity I won't include this. That's really just to zoom in on the fact that your sp2 orbitals kind of go along the same plane and in a triangle, in a trigonal planar shape, so they're all 120 degrees from one another, like a p symbol. Now you have one p orbital left, and remember you have 3 p orbitals in total. That means one p orbital is not being used, and that unused p orbital lies above and below the plane. So I've kind of skewed that, but essentially you have a p orbital above and below, and that's spare, and that can be filled with electrons. So in the case of 1,3-butadiene, what we've shown are the unused p orbitals, and they talk to one another, and they form pi bonds. And this is a pi network because you have 2 pi bonds that can talk to one another. Now in order for this to work, they all must be in the same plane, and there must be conjugation. So we need to remember that word, conjugation. Conjugation means alternating pi electrons, or alternating single and double bonds. It can also mean you have charge in there as well. So instead of a double bond, you can also have a positive or a negative charge. So I want to zoom in on what I mean by positive and negative charge. I'm going to give some examples of conjugated systems which are perfectly allowed. So you can have this system. This is perfectly conjugated because you have a charge, single, and then double. You can also have this situation. You have charge, single, double. So the rule is, as long as the single bonds are separating the pi bonds and the charges, then you're fine. And it has to be just one single bond only. So the way I would read this is double, single, charge. Charge, single, double. Double, single, double, single. Double, single, double, single. Charge, single, double. Those are all conjugated. So as long as the singles are separated and they're separating by 1, that is essentially conjugation. I only gave these 2 examples. These are the harder ones, and I will be covering them later. So if that was confusing, no, don't worry about it, because I will go over that in more detail later on. For now, let's just look at 1,3-butadiene because it's a relatively simple example. You have 2 double bonds. What other piece of information do you need to understand this topic? The number of pi electrons is also important. So the number of pi electrons is twice the number of double bonds. For 1,3-butadiene, you have 2 double bonds. That must mean you have 4 pi electrons. Every double bond has 2 pi electrons. So we need to consider the combination of these molecular orbitals, and the one thing we want to know are how many nodes does each molecular orbital contain? And that's our guideline for constructing molecular orbitals for pi systems. So here we have it. We have 4 different p orbitals. So the number of p orbitals used, 4 in this case, must equal the total number of molecular orbitals, which is 4 again. This mirrors what we saw in the previous component. The number of molecular orbitals can never increase or decrease. It must be conserved. And as we saw before, the number of electrons must be conserved as well. How do we know that this is the pattern for all of our molecular orbitals? And the key to knowing that this is indeed our pattern is to look at the number of nodes. What's a node again? The node, another way to describe it, is a change in phase. Change in orbital phase. So in the case of the first example, we have no nodes, so there are 0 nodes in the lowest energy example. What about MO number 2, the second molecular orbital? This is essentially a pattern. You just have to ask yourself, what pattern can I create that will give me 1 node? And there is only one pattern that can give you 1 node, and that's this one here. So this has less to do with chemistry and more to do with just spotting a pattern. You're told, here's a rule, if you go from white to black, draw a line. How many lines do you have? Draw one with 1 line, draw one with 2 lines, and draw one with 3 lines. So here we have 1 node, because we drew 1 line where the phase changed. What about the second example? Now you need to think, how can I create 2 nodes? You can have a phase change here and a phase change there. And that's the only combination that's going to give you 2 nodes. Oh, wrong pen. 2 nodes. And for the fourth and final molecular orbital, because we only had 4 p orbitals, so you can only have 4 molecular orbitals, you can have 3 nodes, and that's by making everything alternate. And that's a good little trick to remember. For the highest energy one, you want everything to alternate so that you're essentially having a phase change as often as you can, and that will give you 3 nodes. Pink again. So that'll be 3 nodes. So that will give us the number of molecular orbitals. But the last thing we have to consider are the number of pi electrons. How many double bonds do we have? It's 2 times the number of double bonds. Double bonds. And that will equal 4. We have 2 double bonds in our system. Apologies for the handwriting, I'll try and slow down a little bit so that that's clear. So we have 4 electrons in total. Now you just fill them up as always. So you can see you fill up 2 there, then you go 1 level up and you fill up another 2. And that's essentially the structure that we have. Now it looks like you have some molecular orbitals which are occupied and some molecular orbitals which are unoccupied. And I'm going to draw a dividing line here between our occupied electrons which are filled up. Make that clear, that's meant to be an arrow. So these electrons are unoccupied. Are occupied, and this orbital over here contains unoccupied electrons. And these have special acronyms. And the highest occupied molecular orbital is molecular orbital number 2. So this is highest occupied. MO, and it's commonly known as the HOMO for short. And this example here, let's have this arrow coming here. Actually, it's I'll do this arrow a little bit better so that we have space and some clarity. This is your lowest unoccupied. Molecular orbital, and this is called the LUMO. And they might ask you about the HOMO and the LUMO. So the HOMO is basically where you finish filling up all your electrons, and the LUMO is always one above your HOMO. So the LUMO is always one above wherever your HOMO is. So this is how you fill molecular orbitals for organic pi systems. Now in the exam, hopefully they would ask you a simple example, but they might not, so we need to consider this. So the next example I'm going to give is a very difficult example, but I want you all to see this so that you will never get caught out by it. So Cp-, which is C5H5-, it's a very useful ligand in many metal catalyzed reactions. Sometimes these questions in exams, they give you extra information that you don't actually need. You should always separate out or extract what's useful and what's just extra, what's just extra information. What does matter is it binds to a metal center through all 5 carbons of a 5-membered ring. Now that is important. It looks like this is one system, a system of 5 carbon atoms all behaving as one. And as predicted, there would be a resonance structure associated with this. We do have a conjugated system. Charge, single, double, single, double, single, charge. This is indeed a a conjugated system which can have resonance. And I'm going to show one of the resonance forms. You can push the 2 electrons here and then push 2 electrons into this carbon. So I'm only going to show one. And there's a very specific reason why I want to show you one resonance form to help you understand this question. And that's because you can see now that the negative charge essentially dances around the structure. So there's not really any difference between any of these carbons. All of these carbons are equivalent. That's important because it looks like we have communication between different p orbitals. What this diagram is telling us is that you have p orbitals here, p orbitals there, and a p orbital here. It looks like this negative charge is occupying a p orbital. It must do if it can communicate with the other p orbitals. Another way to look at it is, and I'll do this in green because this is a separate point, but it kind of nicely complements the point we've already made. All 5 C atoms are sp2 hybridized, so they must all be planar. So this is valence bond theory revision. Therefore, this implies that we have 5 extra p orbitals, and indeed we do. Now, as in the last example, the key to showing molecular orbitals for pi systems is to know the total number of p orbitals. So I want to show this on an energy diagram. So I'm going to show an energy diagram. You might ask yourself, how do I do the skeletal structure for a pi system? I want to give myself a lot of room here so that my handwriting is as neat as possible. I do definitely want to make sure that everything is very neat as possible. In the previous example, the skeleton for showing this was a line, and the reason it was a line was because we had a linear compound. So our compound was in a line, and we could simply show a line for our molecular orbital diagram. Now we have a ring. As you might predict, we must need a ring template to show our molecular orbitals. So this axis is our energy axis again. What is the lowest molecular orbital combination you can have? Surely that would be the one that doesn't have any nodes. So it must be the one where you have, I'm going to show now the 5 p orbitals that are all talking to one another, and if they're all in phase, you will not have any node. This must be the lowest one. And there's only one combination that would give you this situation. So this is 0 nodes. So that would have to be MO number 1. What about the next level up? You can even start by saying conceptually, that must be the one with 1 node. There's actually 2 different combinations. So this is where it wouldn't get any trickier than this in terms of trying to understand the template structure. Because you have an odd number of carbons, you have 2 situations, 2 combinations, 2 different patterns that will give you 1 node. The first one looks as follows. So you have 2 in phase there and 3 in phase in the front. How can you dissect that at a phase change? You can show, let's solve the actually. There's a node cutting through the ring with that way. Think of it as a window pane cutting through the phase change. That's how you show 1 node. Now, because we have an odd number of carbons, what we do, so this only works for odd number of carbons. In a ring. I'll just show a little asterisk actually, that might be easier. And I want to highlight this carbon. What you do is you discount that carbon, because if you discount that carbon, you will come up with another pattern that will give you 1 node. Now, you do not need to know the reason behind that. You just need to know if you have an odd number of carbons in a ring, so that could be C3, C5, or C7 in a ring. you always discount one carbon to give you another pattern, another arrangement. And this arrangement looks as follows. Because this will allow you to draw a node cutting right through this axis over here. So that's another one, and this is the second molecular orbital. So you have two of them. So that can be very tricky, but I wanted to show this because that's as tricky as it would get. So we're hitting the roof of how complicated this would get. And the last example, now you want to have as many nodes as possible. So we can try and look at this and think, well, what if we just have things alternating as much as we possibly can? So we'll draw our 5 p orbitals again. And we want things to alternate as much as possible. Well, you can have this one shaded, and then you can have these two unshaded, and then you can have this one shaded. So you're going to still have to have two paired up. But let's see where our nodes actually are. Where's the phase changes occurring? You have one node here that perfectly dissects these two and these two, and you can have a crisscross. You can have another node there that nicely dissects that one as well. So there are two nodes. So I'm just going to write inside here, two nodes. As before, we have a situation where you can discount one of the carbons, and this only works for odd numbers, where if you discount one of the carbons, I can just put an asterisk there as well, you have another molecular orbital combination where you only look at 4 of them, and you can come up with 2 nodes again, this way. So I'm creating as many alternations as possible, and this time our nodes are dissecting here and through there. So those are our 2 nodes. So it looks like in total we have 5 molecular orbitals in total, but 2 pairs of them are actually degenerate, they're actually equal energy. So the way to show this is like so. This is for cyclopentadiene, so you have MO1, MO2, and MO3. Question, how many electrons did we have in this system? How many pi electrons were involved? Well, you had 2 here, so this is 2 pi electrons. You also had 2 electrons that became part of the pi system, so this also counts, because they also can form a pi bond through resonance. So this is another trick. If it's in resonance, if it's in conjugation, it's included in the pi system. The negative charge is part of the pi system. They also count as 2 electrons. And you also have 2 pi electrons over here. So in total, we have 6 pi electrons. That's important. We have our empty rooms, now we have our occupants, and we need to fill this up, as we always do. 1, 2, 3, 4, 5, and 6. So you can do a dividing line, and you can say, I have my HOMO and I have my LUMO. So this is your HOMO over here, highest occupied molecular orbital, and here's your LUMO over there. And that would be the diagram, probably one of the more complicated examples of a diagram for molecular orbital theory for organic pi systems.